In this video, we will learn how to describe the physical and chemical properties of phenol. In the first section of this video, we'll look at how we identify phenols. Phenols are organic molecules that contain a hydroxy group bonded directly to an aromatic ring. Aromatic hydrocarbons are unsaturated molecules that are characterized by the presence of the benzene ring. Benzene has the molecular formula C6H6, and its structure can be represented as a hexagon with a circle in the centre. The hydroxy group contains an oxygen atom covalently bonded to a hydrogen atom. If we attach the hydroxy group directly to the benzene ring, we get the molecule called phenol. Phenols are distinctly different to aliphatic alcohols, where we see the hydroxy group bonded to a carbon chain. Phenol is not to be confused with cyclohexanol. Cyclohexanol contains a hydroxy group bonded to a ring structure. In cyclohexanol, the ring structure is saturated, so cyclohexanol is not a phenol. Consider the two compounds shown here as further examples. Here we see molecule A on the left and molecule B on the right. Molecule A is classed as a phenol, since the hydroxy group is bonded directly to the benzene ring. Molecule B is classed as an alcohol. Although molecule B contains a benzene ring, the hydroxy group is not bonded directly to it. Phenols and alcohols do share some similar chemistry. As an example of the similar chemistry of phenols and alcohols, they can both be converted into esters. The molecule commonly known as salicylic acid is easily converted into the ester aspirin by using a reagent called ethanoic anhydride. Ethanoic anhydride is a carboxylic acid derivative. It's made quite simply by condensing two molecules of ethanoic acid together. Aspirin is a common over-the-counter medicine used for pain relief. The ester is formed via the phenol hydroxy group in salicylic acid. The waste product in this reaction is a molecule of ethanoic acid which originated from the ethanoic anhydride. Alcohols react with carboxylic acids in the presence of a concentrated sulfuric acid catalyst to make esters as well. In this particular reaction, the waste product is water. In this particular case, the chemistry of alcohols and phenols appears to be fairly similar. In most cases, however, the chemistry of alcohols and phenols differs greatly. We will now take a look at some of the physical properties of phenol. Phenol is a white solid at room temperature. It has a rather sweet tarry odour that is similar to old-fashioned antiseptics and coal tar soap. If we heat solid phenol crystals to around 41 degrees Celsius, we'd observe that it melts. In fact, phenol has a much higher melting point than other aromatic compounds of a similar molecular size. So how do we explain this unusually high melting point? In solid phenol, the molecules can hydrogen bond to each other. When we melt the phenol, we have to overcome this intermolecular hydrogen bonding. More energy is required to overcome these intermolecular forces than that required in other aromatic molecules where hydrogen bonding does not exist. Phenol is much more soluble in water than benzene. At higher temperatures, it's possible to dissolve about 10 grams of phenol into 90 grams of water. This would result in a solution that is about 10% phenol in water by mass. So why is phenol far more soluble in water than benzene? Just as phenol molecules can hydrogen bond to other phenol molecules can also hydrogen bond to water molecules. This hydrogen bonding allows phenol molecules to fit into the extensive hydrogen-bonded network of water molecules in liquid water. This explains the good solubility of phenol in water. Solutions of phenol in water were commonly known as carbolic acid. In early operating rooms, phenol solution was sprayed around the patient as it was a known antiseptic. In the next section, we'll look at the production of phenol and how it's obtained industrially. Phenol was traditionally obtained by the fractional distillation of coal tar. Coal tar is obtained by heating crushed coal in the absence of air. The vapours formed from the hot coal are condensed in cold water. The condensate contains coal tar. More volatile compounds are found in the coal gas produced by this process. This gas was burnt as a waste product or used to produce energy in the form of heat. Coal tar is in fact a mixture of many aromatic compounds. As well as phenol, it contains cresols or methylphenols. Since these molecules have different boiling points, fractional distillation is used to separate them out. Industrially, phenol is synthesized by reacting chlorobenzene with aqueous sodium hydroxide. The process takes place at about 300 degrees Celsius and the pressure is elevated to about 300 times atmospheric pressure. The initial product in this reaction is sodium phenoxide. The sodium phenoxide is then treated with hydrochloric acid to produce phenol and sodium chloride as a waste product. In the next section, we'll study the acidity of phenol. Phenol can behave as a weak acid in aqueous solution. The hydroxy group can deprotonate. In phenol, the oxygen-hydrogen covalent bond breaks and the phenoxide ion is formed. Water accepts the proton released by the phenol molecule and the ion H3O+ is formed. H3O+ is known as the hydronium ion, sometimes called the hydroxonium ion. The phenoxide anion is a stable ion due to the presence of the benzene ring. Other alcohols, such as ethanol, can deprotonate in a similar way to phenol. The reaction of ethanol with water is very similar. In this case, the product is the ethoxide anion. Since the ethoxide anion is not stabilized in the same way as the phenoxide anion, alcohols are very weak acids indeed. Phenols are therefore stronger acids than alcohols. It's important to realise that acidity is a relative concept here. Phenols are in fact very weak acids indeed. Even carboxylic acids, which are classified as weak acids, are stronger acids than phenol. Carboxylic acids will react with relatively weak bases, such as carbonates, to produce carbon dioxide gas. Since phenols are weaker acids, they will not react with weak bases such as carbonates, and no carbon dioxide gas is produced. Phenol will react with very strong bases. Phenol reacts with sodium hydroxide to give sodium phenoxide. On the other hand, alcohols, such as ethanol, do not react with sodium hydroxide to any extent. If sodium hydroxide is added to ethanol, sodium ethoxide is not formed in any appreciable amount. Another way to produce sodium phenoxide is to heat sodium metal directly with phenol. In this reaction, hydrogen gas is produced which escapes, leaving solid sodium phenoxide behind. The chemistry of alcohols is similar here. If sodium metal is heated with ethanol, sodium ethoxide and hydrogen gas are produced. In the next section, we'll study the nitration reactions of phenol. Phenol reacts readily with dilute nitric acid. Nitric acid has the formula HNO3. In these reactions, a hydrogen atom attached to the benzene ring is substituted for a nitro group. These reactions are known as monosubstitutions. With dilute nitric acid, the products formed are 2-nitrophenol and 4-nitrophenol. If phenol is reacted with concentrated nitric acid in the presence of a concentrated sulfuric acid catalyst, further substitution reactions may occur. The product formed in this reaction is 2,4,6-trinitrophenol. 2,4,6-trinitrophenol is also known as picric acid. Picric acid can decompose very suddenly and exothermically. Large volumes of carbon monoxide steam and nitrogen gas are produced. It's been used as a high explosive. In the next section, we'll see how a plastic called bakelite can be made from phenol. Phenol can be heated with methanol or formaldehyde in the presence of an acid or base catalyst to form a hard brittle plastic. In the first step, the phenol molecule becomes substituted. The substituted phenol product then undergoes a condensation reaction with another phenol molecule. In the condensation reaction, a small molecule, in this case water, is eliminated. The substitution and condensation reactions then continue until a rigid network of molecules develops. The polymer formed is known as bakelite. Bakelite contains a three-dimensional cross-linked network of aromatic rings based upon phenol. Bakelite can be moulded, but it sets upon heating, so it's described as a thermosetting plastic. As bakelite is an electrical insulator, it was used widely in electrical equipment cases such as radios and light fittings. In the next section, we'll see how phenol solutions can be detected chemically using some simple chemical tests in the lab. Phenols react with ferric chloride, also known as iron 3 chloride, to produce coloured complex ions. A solution of phenol in water is generally colourless, whereas ferric chloride has a distinct orange to brown colour. The ferric chloride reacts with the phenol solution to give a violet to purple solution. Other phenol derivatives will react with the ferric chloride in a similar way. The actual colour of the complex ion formed will depend precisely on the phenol compound used. An alternative test is to add a few drops of bromine water to a solution of phenol. Bromine water has a distinct orange to brown colour. When bromine water is shaken gently with a solution of phenol, a white precipitate develops. The white precipitate causes a medicinal or antiseptic smell. The white precipitate contains 2,4,6-tribromophenol. Notice that in this reaction, the orange to brown bromine water will be decolorized. Now it's time to look at a question to test our understanding of the reactions of phenol. Fill in the blank. Phenol reacts with concentrated nitric acid in the presence of concentrated sulfuric acid, forming blank acid. A. Phthalic. B. Salicylic. C. Citric. D. Picric. E. Benzoic. In this question, our starting molecule is phenol. Phenol is an aromatic molecule that contains a benzene ring. When we draw the structure of phenol, we do not normally include the hydrogen atoms that are bonded to the carbon atoms in the benzene ring. Phenol tends to undergo substitution reactions with other reagents where these hydrogen atoms are substituted for some other group. If the reagent concerned is concentrated nitric acid, we get substitutions of the hydrogen atoms in positions 2, 4 and 6 on the benzene ring. We also see that concentrated sulfuric acid is included here. This is present as a catalyst. So for this particular reaction, nitro groups are substituted for hydrogen atoms at positions 2, 4 and 6. The product is therefore named 2,4,6-trinitrophenol. The common name for this molecule is picric acid. Historically, it was used as a high explosive. Although picric acid does not contain an easily identifiable acidic group, we find that the hydroxy group in this molecule can release a proton. This does not happen to any great extent, so picric acid is a weakly acidic molecule. Phthalic acid, salicylic acid, citric acid and benzoic acid all contain carboxylic acid functional groups, which picric acid does not. So picric is the correct answer. We will now review the key points about phenol. Phenols contain a hydroxy group bonded directly to an aromatic ring. An example of an aromatic ring is a benzene ring. Some of the chemistry of phenol is similar to that of alcohols. However, phenol is a stronger acid than alcohols. It reacts with strong bases like sodium hydroxide. Phenol can be nitrated with concentrated nitric acid to make 2,4,6-trinitrophenol. This is also known as picric acid. Phenol is used to make plastics such as Bakelite. Phenol forms a violet solution with iron 3 chloride. This reaction is one possible test for phenols.